Oh man, I forgot my whatchamacallit, my thing of attendance. Is anyone not here? Say your name if you're not here. My son last night was asking, he's like, "Dad, can you hear me?" So I say the only thing I can say at that point, "No." And then my 7-year-old's like, "Hey." Then how could you say that? I was like, "Can't hear you." I don't know. It gives it gives me joy because I'm stupid. But anyway, let me hand back your homework. By process of elimination, I believe this to be yours. Let's see here. It's like I thought I saw you here. You're hiding in plain sight. There we go.
He lived over Jared.
Yeah.
I don't know where he is.
He went to Jared?
I'll call him and see.
Seems logical. Angelina? It's like, wait a minute. You don't have to put him on speakerphone. I don't want to. Nothing good can come of that. Oh, yeah. He's sitting in the other classroom all alone. Yeah.
Before the last test, you told me I could solve a bonus problem from the first test.
I got it. I have not graded any of those. But I do have them. They're in my backpack of things I should remember to grade, along with the test that my online class submitted about 3 weeks ago. But no, I have a backlog of stuff I need to get to.
He's on his way.
Oh, okay, cool. All right, so let me continue with chapter 4. I'm trying to remember what I already told you guys, but we're talking about exponentials and logarithms. So I think last class I introduced the concept of the exponential function. I tried to explain to you that there's something a little bit subtle about the formula that really you need analysis to understand. But that aside, we have calculators, so we can, if I'd brought mine, calculate the values of exponentials at various points, right? And there's another thing we should notice. Like, let's just review the graph, right? So here's x, here's y, and so this point would be what? So I'm assuming that 0 is less than a is less than 1. All right, so the y-intercept is what? 0, 1, right? And let's just make 3 other points of notice. Point over here would be like -1, 1 over a, right? And this point over here, something like 1 comma a, right? So there's 3 particular points on the graph. You could add more, right? But that's all I got at the moment. And one of the things I would make an observation, right? F of x equals a to the x for x in the reals, right? Is an injective, aka one-to-one function, right? Do you agree? I mean, look at it. It passes the horizontal line test for sure, right? If you take a horizontal line, it's only going to cut through that value just once. What does that mean? That tells us that f inverse, and so f is a function from where to where. F goes from the reals, and I'll just put the range over here, 0 to infinity, right? So the inverse function is going to be a map from 0 to infinity to the reals, right? So the domain of the function becomes the range of the inverse function, and vice versa, right? The range of the function becomes the domain of the inverse function. And we know that the inverse function here exists because well, it passes the horizontal line test, right? And so this inverse function for f of x equals to a to the x is called log base a. So log base a is the inverse log base a. And that's the inverse function to the exponential function with base a, right? And what equations define it, basically? Definition. So your textbook defines it like this. It says that y is equal to log base a of x if and only if a to the power y is equal to x, right? So that's the definition that your textbook gives. That's okay, I suppose. I mean, it does uniquely define it, but it's kind of hands-off. I would say more pragmatically, we should notice, I would say, however, I think the following are more useful. All right, in particular, we have log base a of a to the x is equal to x. So log base a of a to the x is equal to x, and that's for any x in the reals. So it doesn't matter, positive, negative, whatever. It's all good. And then also, a to the log base a of y is equal to y again, and that's for y positive. But essentially, these two properties define the logarithm in their relation, in its relation to the exponential function, right? And I would advocate using those to calculate logs, unless you had a calculator, and like you're good at it, right? So let's see here. Can we put a retroactive addition to the graph I started the lecture with? So let's add the graph at this point. Let's add the graph of y equals log base a of x to the graph. What would that look like? So remember, it should be the reflection. Ooh, that's weird. So there's y equals x, right? And to graph the inverse, we can just flip the x and the y coordinates on the original graph, right? So this changes to 1 over a minus 1. So it's like here. Hey, this is nice. And the y-intercept at 1 changes to an x-intercept at 1. And this point here changes from 1a to a1. So it was supposed to be right above this point. Sorry, I'll stop eventually. So it's just like here-ish. So the graph of the logarithm looks something like this. Now, I should mention, though, that all of this assumes that the base is between, this is exactly wrong. What's my base? This looks like 2 to the x, doesn't it? Not 1/2 to the x. So I said this, but what I mean to say is what? What should I say? Base a is greater than 1. That's what I'm graphing right now. right? So this is log base A of x. Let me this might take a minute. I've not logged onto this computer before. Any questions so far? So let me ask you, here's some exercises. I want you to try to calculate log base 2 of 8. I want you to try to calculate log base 10 of 100. And see if you can calculate log base A of 1. So you guys try to work on those while I give this back. Mm-hmm. So how should we do these? So you could go back to the book's definition, but I just think it's better to look at these in the following sense. This is like log base 2 of what? 2 to the what? 2 to the 3. So, that means, yeah, I heard a 3? Exactly. Now, of course, you can look at that. That's because 2 to the 3 equals to 8, right? So that's how this box, the definition I wrote from your textbook thinks about it. But I don't know. I personally have a lot of trouble. Well, I don't have a lot of trouble, but it's just not as linear, the thought process, as this one. I prefer what I wrote.
Can we do it either way then?
Yeah, either way is fine. If you already have completely understood and grasped the boxed definition, that y equals to log base a of x, if and only if a to the y is equal to x, fine. You can use that, It's not wrong. But I think I'm going to teach you to use the log base a of a to the x equals to x strategy, at least for problems like this. Now, sometimes this won't work either, right? Is everything a power of 10? No. Is everything a power of 2? No. I mean, so this strategy can only go so far. But a lot of the questions that we start with are like this, so it's not a bad idea. So 10 is 100 squared, right? I mean, 100 is 10 squared, and so this is what? 2. And what's log base a of 1? 0, because that's log base a of a to the 0, right? So that's 0. Right. And example 4, what's log base a of a? Exactly, it's 1. So really, and I was, I didn't pick a specific choice of a, because one of the things I'd like to emphasize is that these are really, example 3 and example 4, they're not so much examples as they are properties of the logarithm, right? The logarithm of 1 is 0. The logarithm of the base is just 1. So we have that. Now, I should mention the graph of the other see if I can get this thing to work. I'll let the computer do the job here for the other base. If I can find my Chrome, there it is. So let's see here. What does? Come on. Oh, okay, great. Go away. Fine, whatever. So it's trying to add extensions and junk. So here, Desmos. So we look at log base A. All right, so 1 is, are we allowed to have 1 as a base for the log? It is not allowed, right? Let me switch this up here. Let's go from 0 to 4. Step size of 0.5. There we go. Oh, wait, 0.2 maybe. All right, so here we have in green the energy crisis, turn off lights. Okay. That sticker must be from like 1978 or something, I don't know. Let's see here. What happened? Oh yes, we have all the Marys we could hope for are back. Yes. So look, here is the exponential, right? And over here is the logarithm, just like I graphed on the board already, right? What happens when we go to base like a half? What's that look like? So if I put the base back to, or let's say a 6, here's the base 0.6. So base 0.6, of course, the exponential, it goes really small for large x, as I was talking about last class, right? It goes to 0 as x goes to infinity. It goes to infinity as x goes to minus infinity, 0.6 to the x, right? But the logarithm, it's different, isn't it? So in this one, we're going to plus infinity as we approach the y-axis, right? And then it kind of goes off like that. So the graph of the logarithm, when the base is less than 1, is quite different. And in fact, I think almost always when people talk about logarithms, they're assuming a base larger than 1. Actually, it's really weird, honestly, to work with bases less than 1. The only place I think I've ever really seen it is in a pre-calculus book. As far as I can remember, I've never seen an application use a base less than 1. It's really, really weird. Well, this is pre-calculus, so you might. But I mean, past this course, probably not. Yeah. I mean, it doesn't give me joy. I would say you need to know this, need to know to pass. Well, that's a personal question. If I would have to, I need a lot more data. Yeah, but I would say I would focus like 70% on this and like 30% on that. Something like that. What I'm trying to say is, if you hear somebody else talking about logarithms, I would assume by default they're talking about a base larger than 1. That's all I'm trying to say. So.
This may sound like a really stupid.
Whoa. What on earth? Funky, yes.
But what do you use a logarithm for? Like,
Oh man, look at that. I did not know that can happen. Oh, that's cool. Look at that. Base 1.4. Base 1.2, you have the graph of the exponential and the log cross. I did not know that happens. I thought it was always like above and below the line y equals x like this. Because I've only really looked at exponentials of like base 2 or higher in my usual tinkering. So your question is like, what are logarithms good for? That's a great question.
what am I doing?
What are you doing? Yeah, so let's talk about that. So the reason I got this projector out is because I could easily spend 10 minutes making the graph that we were just looking at, and I would still probably not have done a great job. Oops, what happened here? So, I mean, that's a reasonable question. Why are we studying exponentials? Like, what's the point? I mean, you could have asked the same question about polynomials, right? Or rational functions. But those formulas just seem less awkward, right? So it's less of a question people ask. But the applications of the exponential, well, here's a few. So last time I talked about the amount at time t being equal to the principal times e to the rt. So this is, continually compounded interest. That's one reason, right? Remember, in this context, the book says that e is equal to the limit as n goes to infinity of like 1 plus 1 over n to the n power. And so that's a different definition than the one I kind of sketched out last time, which was the exponential is like that base that gives you a graph which has a slope 1 for the exponential function as it crosses the y-axis. But like your textbook takes that as the definition of the number e, right? And so if you take, but I tried it out yesterday in the other section, and if you actually start calculating like 1 plus 1 over 2 squared and 1 plus 1 over 3 cubed and so forth, I did all the way out to like 1 over, I forget what, I think I did 1 over like 100 even. 100. You have to get very far out before you even get to like 2.71. So this description of the number e, it's pretty clumsy. Like you have to go really, really far out to get the number e. But this is the natural base, if you will. This goes on and on. And if I had my calculator, I could tell you what it is right offhand. I guess I could just use this thing here. E. 2.718. 2.718, da-da-da. In fact, I think I could do that numerical calculation really quick here. Say 1 plus 1 over n raised to the n power. Like, oh man, I should have looked up. Hey, why didn't you ask me to add a slider? I want a slider. Come on. Let's go to like 1,000,000. See the formula right there? Check it out. So when we're at, so compare, I don't know if you guys can see it or not, but when we're at like 100, we only get 2.7 matching. If I put n equal to, say, 100,000, I get 2.718, and the 2 matches, and then the 8 doesn't match up, right? The 8 in the actual number is a 6 in the approximation. If I go to like 1,000,000, how many digits do I have? So anyway, I'm just saying you can play around with this and you can see that that limit really does, eventually I think I can get far enough out that I've got, I'm not sure how, well, look at that. Man, it's really hard to get past, check that out. I got all the way out to 2.7182818, 1, and then 8's the next number, but my approximation gets 6, and I can't get that 6 to budge, you know? All right, anyway. I'm digressing. So this was the definition given in the book for the number e, and they derived it from looking at compounded interest, right? So you're like, well, I don't care about compounded interest. Is there like another reason we care about this? And I asked you about exponential functions or logarithms, and you're just talking about the specific number e. Why is that, right? Why am I just talking about e? Because most of the interesting things, so another example, population growth. Population at time t, we could go the initial population times e to the kt. So this is exponential population growth. So that's another place where e to the kt comes up. There's also the number of particles present at time t. So you have the initial number times e to the, well, usually minus kt. And here we're talking about radioactive decay. Right? Radioactive decay, you have particles which are unstable. If you want a formula for the number of particles after time t, you can express it in terms of an exponential, like this. And so why do you want logarithms, right? Well, you could ask an applied question, right? Like, if the population is initially 1,000 frogs, and the growth rate k is equal to, I don't know, 2 with respect to days. I mean, you got to ask, these formulas, the question is like, what are the units on the constants which multiply the times, right? So if you're in a science class, you have to think about the dimensional analysis, right? Like, for this formula to make sense, if t is time, then k has to have units of like 1 over time. Because whatever you feed into an exponential, it has to be like unitless. It has to be like a pure number. That's the way you have to think about it. So when I tell you k is 2, it has to be with respect to some unit of time. So I'm just going to say 2 days, right? So if you suppose you have 1,000 frogs and the growth rate is 2, then I can ask, at what time do you have 10,000 frogs? How many days? In other words, if your frogs are giving tadpoles and the tadpoles become blah, 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 right? I mean, more frogs. How long does it take? All right, so what we can do is we just set it up, right? So we have 10,000 is equal to 1,000 times e to the, what was it? K was 2. And then the time I don't know, right? So in order to solve that problem, I need to know how to solve this kind of equation, right? To solve this kind of equation, I need to understand like properties of exponentials, and actually logarithms are the way to go. So let me solve it right now, even though I haven't introduced all these things to you yet. But first of all, we can divide 1,000, right? So this gives me 10 equals e to the 2t. I mean, I think everybody could already done that, right? And then at this point, I need to introduce another notation. See, definition, log base e is what's called the natural log, ln. And it's the natural log because, well, the exponential comes up in a myriad of applications in the sciences, and so it's natural to talk about this log. And so the natural log has the following properties, like natural log of e to the t is equal to t, and e to the natural log of t is equal to t. So the natural log is the inverse function to the exponential. Inverse with respect to composition of functions, right? So how can I solve 10 equals e to the 2t? Do ln to both sides. That's exactly what we do. Ln of 10 is equal to ln of e to the 2t. Ln of 10 is a number, right? What is it, 2.3025? Okay. And ln of e to the 2t, well, that's just 2t. So what's t equal to? T is equal to 2.3025 approximately divided by 2, which is 1.151. So if you have a growth rate of 2, right, how many days till 10,000 frogs? About 1.15 days. So not long, right? I got a lot of frogs at my house. I'm like, what's that on the window? Jenny's like, it's a frog. I'm like, oh. This is not new to me. Like, I got 3 frogs where I used to live in Virginia, like up on the 2nd story. Like, you get frogs in all the windows on the outside of the house. They're just all over the place. But anyway. Okay, so this log of 10, we couldn't calculate what? We couldn't calculate that using the trick that I had with the previous examples, right? Because it wasn't like natural log of e squared or something, right? But anyway, so we do need to use the calculator is my larger point, right? We will need a calculator to calculate values of logs and exponentials on the next test. But there are also problems which don't use calculators, which use properties of logs and exponentials, so we need to learn those. The properties of exponentials, they've been with us since the start of the course, right? Like, what are the laws of exponents? You guys know the laws of exponents, right? Well, here's another question I should throw at you. Can you calculate log base 3 on your calculator? There are additional, by the way, this is just the start of it. There are other things like where the exponential appears in like a sum in the denominator. If you study like population growth where there's some sort of like limiting population, like your system can only tolerate so much, and then beyond a certain population the growth starts declining, so there's like a so-called carrying capacity to the system, then the solution ends up being something like a constant divided by another number plus an exponential times the growth rate. Like there's other formulas, and it's even like the example in the textbook, which I could not find today to bring over here. Otherwise, I would just write it. There's much more, is all I'm trying to say. So properties of laws of exponents, these you guys already know, right? If I have a to the s times a to the t, we have a to the s plus t, right? 1 over a to the s, a to the minus s, right? A to the s to the t power is a to the st, right? These things I have introduced early in this course, right? We talked about these already. You lost points on these things already, right? Many of you. Laws of logarithms, these are new, right? So let's see here. What happens if we take the logarithm base a of a to the s times a to the t? What do we get? That's the same as log base a of a to the s plus t, right? So that's s plus t, right? Can you write a, I mean, if, what is, how does s and a to the s relate? How can I rewrite I mean, I could say s is equal to log base a of a to the s, right? So with that insight, I can rewrite s plus t as log base a of a to the s plus log base a of a to the t. And here's another thing. So if x and y are greater than 0, then there exists s and t in the reals such that x equals a to the s and y equals a to the t. I say that there exists s and t. Can you tell me which s and t do it? I mean, I'm claiming there exists. What's my choice for s to get back x? I can make s as a function of x and t as a function of y. I'll do x. I'll do the first one. I just use log base a of x, right? And that makes sense because I assumed x was positive, right? So I can take log base a of it, right? Then a to the log base a of x is equal to x again. That's an identity. And likewise, t, I can just make log base a of y, right? So all I'm trying to tell you is I've gone through a kind of meandering proof of the following laws of the following log law. And the law is this: the log base a of x times y is equal to the log base a of x plus the log base a of y. And that is a lot of the reason people are interested in logarithms, is because logarithms convert products to sums. Okay, so in the time before there were calculators, in the time before my time, in my parents' time, when they were in college, they had to use something called a slide rule. And slide rules were actually a mechanical way of calculating logarithms quickly, right? So it wasn't so long ago that we used logarithms as a runaround for calculators. Like it's a way of doing math with very large numbers. Anyway, so that's one property. What's the other important law of logarithms? The other one is that log base a of, say, x to the power y is equal to y times log base a of x. So these are very important. I mean, we could go through the proof of the second one if you wanted. Well, maybe some other day. I think we're a little bit short on time for that. But if you have these two, what could you tell me about the log of a division? How would that work out? We subtract, right? Because division is a negative power, right? So like log base a of x over y would be log base a of xy inverse. So by the first property that we proved, right? And then by the one I haven't proved, but I claimed, we can pull down the power, so minus 1. There you go. So that's another property of logs. So, okay, great. So let me do an example. If I wanted to calculate the log base 2 of, 100, I could do log base 2 of, what's that? That's 10 squared, right? So that should be 2 times log base 2 of 10, which we could even rewrite as 2 times log base 2 of what? 2 times 5, right? So that's 2 log 2 of 2 plus log base 2 of 5. Log base 2 of 2, that we can calculate, right? So this would be 2 times 1 plus log base 2 of 5. So there's an example of the sort of simplification that's possible with these laws of logarithms. Now, at the end of the day, we're still left with the question of how on earth do you calculate log base 2 of 5, right? Right? Because I don't know about, my calculator, it might have a log base 2 button on it somewhere, but I think it's kind of hidden, right? Let's see here. So let's think about this example. What if we had 2 to the x equal to 3 to the x? Could we solve this? So what I usually do when I face a question like this is I just hit it with a natural log, because if you look at your calculator, you have natural log on it. That's easily accessible. So if I take the natural log of this equation, I get natural log of 2 to the x equals natural log of 3 to the x. By the property, by the one I just erased, right? Oh, did I ever pan over there? I think I ever did. I guess everybody's here, though. Almost everybody. Let's see here. I think somebody couldn't come back. They had to go home. But let's see here. So this is x log 2, right? Equals x log 3. Which give me what? So what's x equal to? Oh, no. Nope. Oh, what's this number? You said that number is, what is it? The point is that number is something non-zero, right? This is a number non-zero. Let me call it Pac-Man, right? So x is equal to 0 divided by Pac-Man, otherwise known as 0. X equals to 0 is the solution. graphically, this is very unsurprising, right? Because we talked about the graphs of the exponentials going like this and going like that, right? They crossed at 0, 2 to the x and 3 to the x. This is totally unsurprising that this is the solution.
Will we ever see a problem like that? Just go ahead and smack the 0 off.
It depends on the problem. I mean, it could be, if I put a +2 here, then the solution isn't.
But if we ever see one where it's like a number to the x power equals number to the x power, smack the 0.
It's very likely 0, yeah, in that case. Check this out. Here's another trick. If I have a to the x and I want to rewrite it as e to the x, here's what I do. E to the natural log of a to the x. See, because e to the natural log of any positive constant is that constant again, right? So with this little trick here, I can rewrite a to the x as e to the x times the log of a. I use this trick all the time. But anyway, I will talk to you more about this trick and others next class, because we should next talk about like the change of base formula and start basically just going whole hog into solving the equations. That's really what we're after. Once we get to that, it'll all make more sense. So,
Is that a trick to use us on like tests or a trick to use to help?
yes. What could be more helpful to me than tricking the students, right? Oh, there's a quiz Friday?
Is it? I'm asking.
Yeah, there was a quiz Friday. That's right.